Hi, my name is Tristan Heck, and I'm an undergraduate researcher in Professor Rick Metz's lab at UMass Amherst. I'm here today to talk about work I've done in collaboration with Justine Kozabal involving vibrational spectroscopy of entrance channel complexes of titanium and zirconium with methane. So, what exactly does that mean? Well, let's start with the motivation behind this work. CH bond activation is an important step in the conversion of something like methane, or CH4, to heavier hydrocarbons. The conversion of methane to produce larger ions occurs by sequential reactions of the metal ion with methane. After activating methane, molecular hydrogen can be expelled, leaving MCH2+, which can then react with another methane, expelling another hydrogen and resulting in the formation of a heavier hydrocarbon. This can occur a number of times, up to MCH16+ for tungsten. This is of interest because methane is widely abundant as the main component of natural gas, and converting it into a product that is liquid at room temperature and atmospheric pressure opens up new possibilities for how it might be used. From targeting the transportation sector with an alternative to petroleum to creating a precursor for further chemical synthesis, this work is based on transition metal ions having been shown to be able to activate methane. The two transition metals of interest in my research are titanium and zirconium. So I'm going to talk to you today about the complexes these metals can form with methane as ions in the gas phase. Specifically, I'm going to focus on the entrance channel complexes of the form metal plus with 1 to 4 methanes attached. These are called entrance channel complexes because we're looking at them before they've undergone any actual activation or chemistry, such as changing CH4 to CH2 and a hydrogen molecule, as we mentioned on the previous slide. It is important to understand the thermodynamics of methane activation for both of these complexes, as represented by these potential energy surfaces, calculated at the B3LYP AUG-CC PVTZ level of theory, which is also used for the simulated spectra. In both cases, the ground state of the reactants and the entrance channel complex is high spin, with both showing a significant CH bond activation barrier for the formation of the insertion intermediate. Additionally, in both cases, for the transition state and all further intermediates and products, the lowest energy pathway is the lower spin pathway than the reactants. One major difference that can be noted between titanium and zirconium is that the latter is much stronger at making covalent bonds, leading to a highly stabilized intermediate, minus 112 kilojoules per mole for zirconium versus negative 8.8 kilojoules per mole for titanium. Also different are the overall endothermicities for these reactions to form MCH2 plus H2 products. The reaction for zirconium is endothermic by 31.2 kilojoules per mole, while the reaction for titanium is endothermic by 115.3 kilojoules per mole. Though not directly mentioned in this work, the zirconium complexes were noted to demonstrate CH activation at room temperature, despite this predicted endothermicity. This occurs as methanes are added to the complex without its cooling fully, leaving sufficient energy to overcome endothermicity and result in CH activation. This was not observed for the titanium complexes, which, as we can see, are calculated to have a higher endothermicity for methane activation. How do we go about performing experiments? It starts with an ablation laser, which generates transition metal ions from a spinning, translating metal rod here. Methane and helium and argon for argon-tagged complexes, which I'll talk about in a minute, are passed over the hot ions and extracted into the next stage of the instrument. At the mass gate, here, we select for just the masses of interest to us, that is to say, the mass of our entrance channel complexes. These molecules in the correct mass window make it to the reflectron where they are hit with a scanning IR laser before being reflected back towards the detector. Where the IR laser excites the molecules enough to vibrate and break apart, we are able to detect fragment ions and extract our experimental vibrational spectra. Our experimental spectra look something like this. These are the 8 main entrance channel complexes I'll be discussing throughout this talk. The dashed lines represent the symmetric and antisymmetric CH stretches for bare methane. And as you can see, the peaks in our spectra are often shifted from these. For both metals, you can see the peak at higher wave numbers decreases in intensity with the addition of methanes, disappearing for the 4-methane complexes. This indicates a change in the binding orientation of the methanes that I'll point out later. Here, we can see an overlay of the experimental spectrum for our first complex, titanium methane argon, with a simulated spectrum. Since the methane is too strongly bound to the metal for us to dissociate it under the conditions of our experiment, we argon tag it in order to measure the spectrum without perturbing it significantly. The simulated spectrum, shown in red, is calculated using the Gaussian software package at the specified level of theory. That's B3LYP OG CC PVTZ. The two main peaks in the spectrum represent the symmetric proximate CH stretch, that's at 2789 wave numbers, and the free distal, that is the hydrogen pointing away from the metal, CH stretch at 3026 wave numbers. We can see that theory provides a reasonably good prediction of our experimental results. The optimized geometry for this complex, corresponding to the simulated spectrum, is shown as well. We can clearly see that 3 hydrogens on the methane are pointed towards the metal. We call this A-3 hydrogen coordination. We can confirm this optimized geometry from our experimental spectrum, since the peak at 3026 wave numbers is indicative of this coordination. Here's the same experimental and simulated spectrum, this time for titanium with 2 methanes. Once again, we see the 2 characteristic peaks, and our optimized geometry tells us we have A-3 coordination. See the 3 hydrogens pointing at the metal. This agrees with what we see in the experimental. Remember, this peak is indicative of this A-3 coordination. Moving to the titanium 3-methane complex, we see a decrease in that higher wave number peak that we said was indicative of A-3 coordination. And sure enough, if we look at our optimized geometry, we see that one of the methanes has only 2 hydrogens pointing to the metal. We call this A-2 coordination, while the other 2 methanes are somewhere between 2 and 3 hydrogens pointing at the metal. The breadth of the peak in the experimental spectrum suggests to us that these methanes can interconvert which is fully A-2 and which are between A-2 and A-3. Finally, we get to the titanium 4-methane complex, and we see our higher wave number peak has disappeared entirely, and our geometry appears to be predominantly A-2. The resolution between different peaks in the simulated spectrum is a result of 2 distinct titanium-carbon bond lengths for these methanes. In experiment, however, the broad peak tells us that these methanes are likely interconverting between those bond lengths, smoothing the individual peaks in the simulated spectrum into a single broad peak in the experimental. Our zirconium single methane complex looks similar to that of titanium, and once again we've had to argon tag it in order to get a spectrum. The optimized geometry predicts A-3 methane hydrogen coordination, that's the 3 hydrogens pointing at the metal, and this is upheld by this peak around 3000 wave numbers in our experimental spectrum. Things get a little more complicated for our zirconium 2-methane complex, since it also needed to be argon tagged in order to take its spectrum. However, in this case, our argon tag somewhat perturbs the spectrum and the optimized geometry seen here. While the optimized geometry of the untagged complex predicts the metal and carbons to be collinear, so all on a line and with A-3 coordination, that is not the case for the tagged complex, which sees near A-3 coordination for the methane further from the argon tag, but closer to A-2 coordination for the methane near the argon tag. Similar to titanium, the zirconium 3-methane complex predicts 1 A-2 methane and 2 methanes between A-2 and A-3, which, again from the breadth of our experimental peak, are expected to interconvert readily. And remember, we still have this higher wave number peak in the experimental spectrum, which is representative of this nearer to A-3 coordination. Finally, we have the zirconium 4-methane complex, which, similar to titanium, exhibits a distorted square planar geometry, with predominantly A-2 binding. The lack of a higher wave number peak in the experimental spectrum confirms this, And once again, the breadth of the peak here suggests that interconversion between methanes at different bond lengths is occurring. It is worth noting, however, that we do get some resolution in the experimental peak between the symmetric and the antisymmetric CH stretch contributions. This is not the case for our titanium spectrum. As we can see, investigating these entrance channel complexes not only gives us valuable information about their structure and chemistry, but we are also able to learn more about their chemistry and ultimately their potential for CH activation. Further work will investigate the various products of this CH activation, where it occurs, as well as the properties of similar complexes with other metals. Ultimately, this work connects to the ongoing efforts to convert methane from natural gas into other useful products, as we previously mentioned.